Hi everyone, I'm one of the member of BoW team in TrueChip. Today in this webinar, I'm going to present the PPT for bunch of wires, the node that ties chiplets together. The bunch of wires specification defines a versatile, open and interoperable physical interface between two chiplets or chip scale packages in a common package. It addresses the projected growing demands of compute, memory, storage and connectivity across the entire compute continuum spanning cloud, edge, enterprise, high performance computing and handheld segments. BoW provides the ability to package dies from different sources including different fabs, different designs and different packaging technologies with very low peak power, that is between 0.5 to 1 picojoule per bit for doubly terminated modes, 0.25 to 0.5 picojoule per bit for unterminated. Very low latency, that is 2 to 4 nanoseconds without FEC, less than 15 nanoseconds with FEC from logic interface to logic interface. So here are the BoW layers. So where we have protocol layers for both the chiplets, chiplet 1 and chiplet 2. So the protocol layer that can be any standard protocol, that is like CXL and PCI, and these are the layers for BoW protocol: transaction layer, link layer and physical layer. And here are the interfaces for the layers, like system interface, which is the interface between the protocol layer and transaction layer. The transaction link interface, which is the interface between the transaction layer and link layer. And link physical interface, which is interface between link layer and physical layer. And the main interface, that is called BoW interface, which is between physical to physical layer. So here are the BoW layers: a protocol layer that defines communication between SoC IPs using industry standard or proprietary protocols, for example AXI, PCI, etc. A transaction layer that translates between protocol transfers or protocol packets defined by a bus protocol and individual transaction streams, and that manages the flow control of those individual streams. A link layer that converts between the individual transaction streams and a single bit stream transmitted between chiplets. A physical layer that performs the physical transmission of the single bit stream as defined in the BoW 5 specification. Here are the BoW interfaces. The first one, system interface, which is the interface to the SoC as defined by various bus protocols. The second, transaction link interface, which is an interface between the transaction layer and the link layer. And this interface is not defined by this specification and is implementation specific. Link physical interface, the interface between the link layer and the physical layer based on the slice logic interface as defined in the BoW 5 specification. The BoW interface, which is the electrical interface between the TX and RX files as defined in the BoW 5 specification. So this is the BoW utilization. The transaction and link layers along with the BoW physical layer create a complete die-to-die solution for die disaggregation, where a monolithic SoC is divided into a set of constituent chiplets as illustrated below. Like we have monolithic SoC for which we have on-die interconnect, and for disaggregated chiplets we have BoW interface. So here are the BoW advantages. In order to ease system integration, the following goals were adopted for the die-to-die interface. Simplicity, build on the BoW physical layer, focus on die disaggregation and eliminate complexities of CDR, CRC, retry, etc. Low latency, enable aggressive implementation techniques and use FEC to eliminate serialization overhead of CRC. Scalability, support for different lane data rates and number of slices. Portability, enable interfaces to be built with different implementation methodologies and in different process technologies. Extensibility, create a modular framework that can easily add features over time. Now we have BoW die-to-die packet flow, for which we have two chiplets, chiplet 1 and chiplet 2, and we are taking chiplet 1 as transmitter, for which we have these three layers: transaction layer, link layer and physical layer. So the transaction layer do the functionalities flow control, CDC, packetization, TLP flow control, and the link layer do the functionalities error protection, quantization, selection, packing, assignment, and physical layer do the functionalities serialization, transmission. For receiving side, we have these three layers for which physical layer do the functionalities of reception, deserialization, and link layer do the functionalities for error alignment, unpacking, steering, error correction, and transaction layer do the functionalities for TLP flow control, depacketization, SI flow control, CDC. So here are the packet flow. Functions are performed by the transaction layer. So we have TX interface transaction layer that implement bus protocol responder functionality and flow control on the system interface. Packetize information received on the system interface into transaction layer packets and classify the TLPs into classes and streams that manage flow control for each stream with the far side RX interface. And we have RX interface transaction layer that manage flow control for each stream with the far side TX interface. Depacketized TLPs into system interface information that implements clock domain crossings between the RX interface clock domain and the system interface clock domain that implements bus control requester functionality and flow control on the system interface. Now let's see how the packet formation is going on. From protocol layer, we are getting a packet in which we are adding TLP header in transaction layer, then moving to link layer, we are adding check bits, and then we are dividing our packet into 32 bits granule, then we are adding LLP header and making the packet 512 bits size. And then we are sending the packet to the file layer, which depends upon the fragment size. Okay, so let's have a brief about transaction layer. The transaction layer is responsible for communicating information transferred on the system interface via transaction layer packets or TLPs or on the transaction link interface. A TLP is identified by its TLP type and consists of a TLP header which contains type and auxiliary information, and a TLP payload which contains bus protocol information. The minimum TLP payload size is 14-bit. Individual TLP streams implement credit-based flow control between the TX and RX interfaces and are non-blocking with respect to each other. System interface. System interface transfers information between the transaction layer and the on-die system interconnect via one or more bus protocols. Bus protocols may define one or more bus protocol channels and some number of additional sideband signals, and each bus protocol may specify its own flow control mechanism. To support a particular bus protocol, the transaction layer must implement the required channels, sideband signals, and the flow control mechanism for this bus protocol. This specification recommends that the total latency from the transmit system interface to the receive system interface should be less than 10 nanoseconds. So here we have transaction layer packets for which we have TLP header which is of 12 bits. So we can see in this packet 0 to 4 bits are aux, 5th bit which is reserved, and 6 to 11 bits which is type. The type field encodes the TLP type, which implies the TLP stream and TLP class. For the common TLPs defined by this specification, the following table lists each TLP stream, TLP type, and TLP header. So here we can see in the transaction layer packets we have different TLP classes, different TLP streams, and different TLP types for which we have different encodings. So as we can see in this table, for encoding 00 we have idle type, for encoding 01 we have credit type, for encoding 02 we have message type, for encoding 04 we have virtual wire, and for the rest of the encodings all the TLP types are reserved. So here is the idle packets. For an idle TLP, the aux field is reserved and must be zeros. So this is the idle packet which is of 14 bits where all the bits are zeros, and the aux fields which are reserved which are of 5 bits. So this is the credit packets. A credit TLP grants up to 255 credits for a specific TLP type and support for credit TLPs. For credit TLPs, the aux field is reserved and must be zeros. So this is the format of TLP payload where we can see the packet is of 14 bits and we have 8 bits of number of credit and rest of the bits are TLP type, and for the same packet the aux fields are reserved. So this is the message packets. The message TLP transmits miscellaneous information from the TX interface to the RX interface. A message TLP is transmitted when 16-bit message data are written to a memory mapped register in the TX interface. When a message TLP is received, the message data update a memory mapped register in the RX interface. For message TLPs, the aux field contains 2 bits of message data. As we have seen in the previous packets, the aux fields were reserved, but for this, the starting 2 bits are message data and rest of the 3 bits are reserved for aux fields. Additional message data is captured in the TLP payload. So here is the packet which is of 14 bits and all the bits are zeros. The reserved aux bits can be used to support up to 8 message types. Software or hardware may use these to exchange information in band. So this is the virtual wire packets. The die-to-die interface supports the transmission of level sensitive signal transitions on virtual wires from the TX interface to the RX interface. A maximum of 1024 virtual wires can be supported. So here we can see the format of the virtual wire TLP payload. So here is the packet of 14 bits, and where we can see the 10 bits are VWLD and the rest of the 3 bits after the 10 bits are reserved, and the last bit which is level. The level bit in the virtual wire X packet indicates the level being transmitted and distinguishes between virtual wire level 0 and virtual wire high level 1 packets, while the VWLD field identifies the virtual wire to which the level corresponds. The remaining bits are reserved and must be zeros. So here we will have a brief about link layer. The link layer of the die-to-die interface is responsible for translating TLPs into link layer packets or LLPs, and for mapping the LLPs onto the available physical layer phi slices. This layer also performs error detection and correction. Each functions are performed in parallel to achieve low latency. So now we have error protection and quantization. So the formats of these small and large code words. So we can see here we have two formats. First one is for small code word, where we also have TLP header, and the second format which is large code word. So first format, which is small code word, we can see we have a 32-bit of packet where the first 6 bits are small check. After that, the 6 to 19 bits are TLP payload, and the rest of the bits 20 to 31 bits are TLP header. And we have also seen before that the TLP header have a 5-bit aux field. So the second one is large code word, where we can see the packet is of 128 bits where we don't have TLP header, and the starting 8 bits are large check, and the rest of the bits 8 to 127 bits are TLP payload. So now we have selection and packing. A quantized TLP becomes eligible for transmission when a credit is available. The TX interface selects eligible quantized TLPs to pack into an LLP, which consists of a 32-bit header and 480-bit of payload for a total of 512-bit. The payload is packed as a series of TLP granules. So the LLP format, TLP may start on any LLP granule. A TLP must be transmitted in contiguous granules, including TLPs that span 2 or more LLPs. Idle TLPs may be inserted between complete TLPs. So here we have LLP format. So in the format we have 512 bits. So where we can see that we have 32 bits of header, and rest are G01, G02, G03 and so on, that represents an LLP granule within the LLP. So this is the LLP header format, where we have 32-bit of LLP header, in which the first 6 bits are header check. After that, the 6 to 20 bits are TLP start, and after that the rest of the bits 21 to 31 are reserved. Within the LLP header, the 15-bit TLP start field indicates where a non-idle packet TLP header is located in the LLP. That is, bit 20 corresponds to G01, bit 19 corresponds to G02, and so on. The 6-bit header check field contains the check bits for the LLP header. All other bits are reserved. Bit 21 is reserved for a continuation bit from the previous LLP. So now we have assignment. Once an LLP is packed, the granules in the LLP are assigned to fragments which represent the data width of the interface on an individual phi slice based on the phi serialization ratio. The LLP header is always assigned to the least significant bits, that is 32 bits of fragment 0, and the remainder of the LLP granules are assigned. So here in the table we can see that the phi layer can have different multiple number of slices, that could be 1 slice, 2 slices and 4 slices, and also the phi layer can have different fragment sizes like 64 bits, where the 64 bits of data will be transmitting from link layer to phi layer, and 128 bits where the data of 128 bits will be transmitting from link layer to phi layer, and 256 bits where 256 bits of data will be transmitting from link layer to phi layer, and also there can be different serialization ratio like 4, 8 and 16. So according to the number of slices and fragment sizes, the data size could be different. Like for the fragment size 64 bit, if the phi layer has one slice, then the data of 64 bits will be transmitting from link layer to phi layer. For 2 slices, data will be of 128 bits, and for 4 slices, data will be of 256 bits. And for the fragment size 128 bit, if the phi layer have one slice, then the data of 128 bits will be transmitting from link layer to phi layer. For 2 slices, data will be of 256 bits, and for 4 slices, the data of 512 bits will be transmitting from link layer to phi layer. And for fragment size 256 bits, if the phi layer has one slice, then the data of 256 bits will be transmitting, and if the phi layer has 2 slices, then the data of 512 bits will be transmitting. So here is the training. The link layer trains the die-to-die link to ensure the proper delivery of data. Performed after reset, training entails transmitting a non-data pattern from the TX interface and aligning the data pattern in the RX interface. So here is the alignment that occurs at 2 levels: granule phase alignment within a fragment, fragment skew alignment within a bundle. TX interface drives a sequence of 0 to 255 in each byte of each granule of each fragment. The received sequence is sampled on the RX interface to determine the granule phase and fragment skew. A 256-bit fragment consists of 8 cross 32-bit granules, so the training sequence cycles through a minimum of 32 fragments. For a given slice, the BoW phi is responsible for training the individual lanes with respect to the short synchronous clock. So here we can see the training pattern waveform. Now let's move to the TX interface and controls. So here are the active slices that can be of 1 slice, 2 slices and 4 slices, and the fragment size which could be of 64-bit, 128-bit and 256-bit. And these are the states: TX idle state, that transmitting idle LLPs, TX train state, that transmitting training pattern, and TX run state, that transmitting data. And here for RX interface and controls. So the active slices that can be 1 slice, 2 slices and 4 slices. Fragment size that can be 64-bit, 128-bit and 256-bit. And these are the states: RX idle state, that ignoring data; RX train state, that sampling training pattern; RX wait state, that waiting for sync LLP; and RX run state, that receiving data. So here is the BoW phi slice. BoW is an energy efficient, easy to use phi interface between a pair of die inside a single package. The BoW phi is defined as a single unidirectional slice. Multiple slices are combined to create links of the desired throughput. A link may be symmetric, asymmetric, or unidirectional. A BoW PHY does not have enough drive strength for off-package interfaces, nor is it designed for buses that are entirely on die. A BoW PHY slice either transmits or receives 16 bits of data between die. The BoW is a source synchronous PHY, and each transmitting PHY slice transmits a complementary clock signal with the data. So here is the die-to-die package. So here we have chiplet A and chiplet 2 that are includes in a single package which are connected through BoW interface. So these are the BoW wire and modes. Within the package, the BoW data path is transported on physical passive wires between the pair of connected die. A BoW mode defines the speed of clock and data of the PHY on the die-to-die wires. So here are the different BoW modes. So the clock frequency for BoW 32 is 1 GHz. The clock frequency for BoW 64 is 2 GHz. For BoW 128, the clock frequency is 4 GHz. And for BoW 256, the clock frequency is 8 GHz. For BoW 384, the clock frequency is 12 GHz. And for BoW 512, the clock frequency is 16 GHz. So here is the logic interface where the link layer transmits the data with 16 cross n size passing through the serializer, then analog data path and moving to the receiving analog data path, and then deserializer and transmitting the data to link layer. So these are the signal definition. So clock with 2 wires, data with 16 wires, FEC with 1 wire and auxiliary with 1 wire. So here we have BoW bidirectional slice block diagram for which we have two chiplets, chiplet A and chiplet B, where both can behave as transmitter and receiver. So here we have BoW physical configuration where we have wires, slice, stack and link. The signal traces in the package between the chiplets are called wires. A slice is the basic unit of a BoW PHY. A stack is composed of one or more slices stacked from the chip edge towards the center. A link from one chiplet to another is composed of one or more stacks placed along the chip edge. A link may be configured with equal numbers of RX and TX slices, or it may be asymmetric or one-way. So here are the bit ordering. The PHY TX serializer shall order data this way. On the first clock edge, 16 bits are sent on wires. On the second clock edge, next 16 bits are sent on wires, and so on. Then the cycle repeats. A TX-RX link should be brought up as the link controller asserts PHY reset B to the PHY slices on both ends of the link. The link controller de-asserts PHY reset B to the TX PHY slices, including bidirectional slices, which will be used as TX slices. The LC performs any needed configuration of the TX PHY slices via the APB interface. This is implementation dependent. The LC enables the TX slices if necessary. Once its outgoing clock and P clock stabilize, each TX PHY slice asserts PHY ready to the LC. When all TX PHY slices are ready, the LC signals the TX link layer to send the training pattern specified by the RX PHY. The link controller de-asserts PHY reset B to the RX PHY slices, including bidirectional slices, which will be used as RX slices. The LC performs any needed configuration of the RX PHY slices via the APB interface. This is implementation dependent. The LC enables the RX slices if necessary. Each RX PHY slice performs clock and data alignment and signal PHY ready to the LC when done. When all RX PHY slices are ready, the LC signals the TX and RX link layers to proceed with channel bonding. So here is the redundancy. If none of the physical lines are defective, aux or FEC must be unused. If only a single data line is defective, all data lines logically equal to or below the defective line must be downshifted by 1. Unless aux is defective, this implies that logical D0 would be carried on the physical aux line. If two data lines are defective, all logical data lines equal to or below the lowest defective line must be downshifted by 1, and all logical data lines equal to or above the highest defective line must be upshifted by 1. Unless aux is defective, this implies that logical D0 would be carried on the physical aux line. So here we can have a look on the waveform where we can see the data transfer from die 0 to die 1. Thank you.